Welcome to another Matlab tutorial with Coding Like Mad. Today we are going to be looking at how to do three-dimensional plotting in Matlab. So this is a common task when you want to visualize data that extends into the third dimension, and it's something that Matlab is actually pretty good at. So, to demonstrate, we're going to be looking at how to generate simple 2D color maps. We'll also be looking at how to make contours, and last we'll be looking at surfaces, and then we're going to revisit scatter plots, which is something we looked at in our basic MATLAB line plotting tutorial, and we'll be extending that into a third dimension as well. So, to begin with, we're going to need some data. So in order to generate data in 3 dimensions, I'm going to use something called the mesh grid function. So as you can see on screen, I have generated 2 arrays which go between -1 and 1 with a spacing of 0.025. I then use the mesh grid function to generate a set of grids in X and Y that have the spacing specified by these 2 arrays. To show you what I mean, we can take a look at the size of the variables generated. So xp and yp, which were my prototypes, have dimensions 1 by 81 each, and then x and y are 81 by 81. In other words, x and y are the x and y coordinates on a grid with the spacing given by these 2 arrays. Next, we need a third dimension. To do this, I'm going to use a simple polynomial that's a function of x and y. This polynomial, called zval, is basically a cubic that I picked because it looked pretty nice. So the first way that we can visualize this three-dimensional data is using the imagesc function. As you can see here, it can be just as easy as running imagesc on zval. So this will automatically scale the data in zval in order to make it easy to interpret regardless of the magnitude of the values. Additionally, we're going to use a color bar in order to tell us exactly how to interpret the colors in the plot. There are simpler functions, like I believe there's a image function as well, for example, but I've actually in practice never needed to use it, so I'll just tell you about the stuff that's actually useful for me. So, if we run these commands and I pop the window in so you can see it, we can see that indeed this polynomial is relatively pretty, at least I like to think so, and it has regions where there are peaks in the corners and some slow gradients and some fast gradients and a color bar key telling you how to interpret the colors. So here you can see that zval went between about -6 and +6. One of the things that you might notice is the y-axis is a little bit strange. You might have expected it to start with 0 at the bottom rather than 0 at the top, and you might also have expected it to increase going upwards as opposed to going downwards. This is a convention in MATLAB that I think probably is coming from the days when this functionality was mostly being used by graphics experts who have a coordinate system that's defined in the top left side of the screen and actually has the y values increasing as you go down the screen. It's a little bit confusing to begin with, and it can be especially dangerous if a function uses this convention and you're unaware of it. So meshgrid, just so you are aware, has such a convention inside it. There's a version of meshgrid called ndgrid which does not have this convention. Okay, so let's look at how to plot this data in a little bit more detail. So the first thing is, remember that our variables really were on a grid between -1 and 1, but here it's between 1 and 81. We never told it anything about where these data points were, we just gave it a matrix 81 by 81 of data points. So to tell it where the data actually is, we can give the coordinate scheme like so. And now you see that the y-axis goes between -1 and 1. And it still is increasing going downwards, but at least it has the right units. So this is one very easy way to visualize three-dimensional data. Another thing you might like to do is make a contour plot. So for example, we can just use the contour function on the data directly. And you'll notice that the y-axis is now behaving in the opposite way to the way it did before. This is something that you have to be a little bit careful with, and sometimes if you're not cautious, you may end up mixing these two conventions and it will give you incorrect figures. So it's always good to visualize things and make sure they make sense with the specific data you're working with. So here you can see that these contours were generated and have colors associated with the value of the function in those locations. I can switch from the contour command to the filled contour command to get a slightly prettier map. So I think this is quite appealing. It's a beautiful color palette and everything just kind of looks nice. Like before, we can add a color bar in order to get the scaling of the function. What is particularly nice about Matlab is I can mix these two schemes together. So here I got constant values, whereas I could also get the lines, but why not actually get the imagesc output, which is a continuous variable, with the lines? How would we go about doing that? Well, from the basics tutorial, remember that I'm able to freeze the axes of the system using the hold on command. So if we do that, I get a blank canvas. And the first thing I'm going to do is I'm going to generate my contours again, still a function of zval. We're going to give them x and y coordinates this time to make sure that all of our coordinate schemes match up. And I'm also going to tell it to use a black solid line for its contours. The idea being that we just want to visualize the regions, the color itself would just fade into the background. So it's important that it not be the same color scheme that it uses by default. And then last, we can just plot imagesc zval directly on top as we did before. Oh, we have managed to erase that. There we go. So it's important you get this in the right order. And now we have contours that nicely show each of the regions, but you also get this nice continuous gradient on top. And I think this is a really nice, appealing way of viewing this data. Okay, so this is all ways of viewing three-dimensional data, but actually all of them were two-dimensional, right? We're using color maps. So what if I really want to view the 3D structure here instead of translating the z-axis into a color? Well, we can use another command called surf to do this. However, if we try to do it right now, this is actually very dense data. So let's drop the density of the data down. And we're going to do that just by rerunning this first section of code. And we're going to drop the sampling from 0.025 to 0.05. And having done that, let's use the surf command in order to generate a new figure. So we're going to turn hold off because it was hanging around. And we'll use the surf command now. And what this is going to do is this will actually make the three-dimensional surface of this function. And there it is. So I can view the 3D surface by using the rotation command. And I hope this makes it a little bit easier to visually interpret what's going on. I find that if you're looking at the 3D surface and it's not moving a bit, it's a little bit hard for your eyes to process. So now, if I just viewed this top-down, it would look, I think we need it in this orientation, it would look like we saw it before. But if I tilt back, I can actually see that the z direction is encoding the value of the function. So not only is the color doing that, but so is the coordinate value. And as before, we can put a color bar on, and if you recall from the basics tutorial on plotting, we can, for example, make the font size a little more appealing in order to make this a little bit easier for you to read. So exactly the same information that we saw all of the other times, but with a little bit more, I think a little prettier. And so this is useful if your data is on a regular grid. But what happens if you just want to visualize the data points? What if your data isn't on a grid? What if you just have some data? So let's look at how to make scatter plots in 3 dimensions. So if you recall from the previous tutorial, we had a command called plot available. So I can plot the data in x and y as if it's a function, and there it is. And this is a 2-dimensional plot. I didn't give it any 3-dimensional information. There's another extremely useful command, though, called scatter, which will also generate a similar plot, except this time it's generating, by default, solid circles rather than the x's that I told plot to do. So the scatter command is actually a pretty useful one, I found, and there's some cases where you could do the same thing in plot, but it's a little bit harder to give it the information. Particularly, what scatter is good at is that you can manipulate the size and the color of the data points a lot more easily than you can do in the plot command. So let's try first manipulating the size here. So what if I made the points size 20? You can see that they've now shrunk. I could make them size 10. Now they're even smaller. Alternatively, I have the opportunity to also change the color. I can, for example, make them red instead. The use of the color red here might not work in all versions of Matlab. For sure it works in Matlab 2016 though, which is the one I'm using. So if you find any of this breaks, I would suggest you first think about whether it's your version of Matlab doing it. All of this was possible in 2012 one way or another, I think, though. So you might have to work around it, but it should still be possible. So let's try encoding the function value in the color. This is probably the easiest way to visualize this. And you see we get exactly the same function we had before, except now the color is changing. And we can generate a color bar. And again, we are in good position. You'll notice that the axes, though, really do go -1 to 1. So the axes make more sense than they did with imagesc. So this is an appealing aspect of this. We can also make 3-dimensional scatter plots as well. So this has no more information than imagesc did. It's just that it doesn't break if x doesn't form a grid. So I can, for example, use the plot3 command in order to plot all of my data in 3 dimensions. And here we see again that surface just expressed in terms of x's. But all of my value information is now entirely encoded in the z height. So like I said, one of the nice things about scatter is that the 3-dimensional version of it lets you manipulate the color as well as the size. So, for example, let's make the z value of scatter 3 control the height, but also control the color. And if you do that, now we get what I think is probably the nicest looking plot that we could generate here. It's got quite a bit of information encoded in the color, as well as very nice variations between -1 and 1. And if you want to make it a little prettier, we have all of the usual options. We can create a color bar, we can manipulate the font size, we can add X labels and Y labels, and we can title or even a Z label, and we can of course, add a title to the system and do all of that and generate what I think is a very nice graph. So in a future tutorial, I'll talk about how to create animations here, but I think that this is probably enough for today. If you like this type of content, please consider subscribing to this channel. If you like this particular video, you can give it a like, so I will know that somebody appreciated it, or alternatively, if you have some comments, constructive or otherwise, please feel free to leave them in the comments below. Thank you so much, and I hope you have a lovely day.